Welcome to the first applied mathematics seminar of the series. This is joint with the Leeds Institute for Fluid Dynamics. So it's a real great pleasure to welcome today Professor Nigel Goldenfeld, who's a Swanland Endowed Chair at the University of Illinois at Urbana-Champaign. Nigel is also Director of the Institute for Universal Biology. Nigel did his PhD at the University of Cambridge in 1982, and then was a postdoc at the Institute for Theoretical Physics in Santa Barbara from 82 to 85 before moving on to Illinois. Nigel has a large number of awards. If I listed them all, he wouldn't have a time to give his talk, but he won this year's Leo Kadanoff Prize of the American Physical Society and is a member of the National Academy of Sciences. Nigel is an expert on emergent and collective phenomena, patterns in topics ranging from high temperature superconductors to biology. Nigel was responsible for helping the governor of Illinois to come to a decision for an early shutdown in Illinois in this year's COVID crisis, I think thus saving many, many lives. He's the author of a famous book on phase transitions and the renormalization group. And of course, he's recently turned his interest to fluid dynamics and in particular turbulence. He's PI on a Simons Foundation grant on revisiting the turbulence problem using statistical mechanics. And today he's going to talk to us about the life and death of turbulence. Thank you, Nigel.
Thank you very much for that kind introduction, and thank you for inviting me. So good morning to everybody, or good afternoon where you are. So let me get started and start off with an apology. I'm a poor choice to start your applied mathematics seminar since I'm actually a physicist. So I hope you'll forgive me for that. So let's start then with the problem of turbulence. So everyone knows that it's the greatest unsolved problem in classical physics. So the question that I want to ask is, how would we know if we had actually solved it? What would it mean to solve turbulence? And so that's really behind the things that I'm going to discuss here. And what I aim to show you is that we should be moving the goalposts about what we mean by solving turbulence in a couple of different directions and connect them together in a way that I think is quite novel and interesting from the perspective of statistical mechanics. So I've listed on this front page here my collaborators and my support, and this image is from a paper that I'll talk about later on. So let's get started then with some propaganda. So for theoretical physicists, it's mandatory to have a slide or two about Richard Feynman, so we may as well get it out of the way and over and done with. So in the Feynman Lectures in Physics, Feynman in volume 2 derives Navier-Stokes equations and talks about some of their properties. And I want to just go through what he says here. He says, we've written the equations of water flow. From experiment, we find a set of concepts and approximations to use to discuss the solution: vortex streets, turbulent wakes, boundary layers, and so on. When we have similar equations in a less familiar situation, and one for which we cannot yet experiment, we try to solve the equations in a primitive, halting, and confused way to try to determine what new qualitative features may come out, or what new qualitative forms are a consequence of the equations. And I've highlighted the word qualitative because Richard Feynman is famous for, he won the Nobel Prize for the quantum theory of electromagnetism, and that theory is in fact our most accurate theory. You can get agreement between theory and experiment to something like 10 decimal places. It's quite unprecedented. So Feynman is the quintessential quantitative physicist, but here he's talking about qualitative features, and that distinction is important. And then he says, the next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations. Today we cannot. Today we cannot see that the water flow equations contain such things as the Barbour pole, structure of turbulence that one sees between rotating cylinders, in other words, Taylor-Couette. And then he talks about Schrödinger and frogs, musical composers, morality, and so we'll leave that to Feynman. But the point I want to make is that this whole notion of the qualitative behavior of matter is exactly the domain of statistical mechanics. And so the goal in this talk is to expose the qualitative content of the equations of fluid mechanics, trying to understand the phase diagram, universality, and the scaling laws of turbulence. And we've been able to make a start on that. I'm going to show you today two novel predictions and perspectives that all come from statistical mechanics, partly on transitional flows and partly on what I'll call fluctuation dissipation relations concerning a fluid flow well above the laminar-turbulence transition and heading into the fully developed regime. So let's start very simply with classical mechanics. So everybody knows how to solve deterministic classical mechanics of many particles in a box. You simply solve Newton's equations of motion on a computer, and it's an undergraduate exercise to do that and to find very quickly that this system obeys statistical mechanics, and you can derive many of the properties of statistical thermodynamics very simply from that. So now let's take the number of particles to infinity. So now we have a field, and the equations of motion for that field are just the Navier-Stokes equations supplemented by incompressibility. And so it should be no surprise that these deterministic equations can also have stochastic solutions and will obey some form of statistical mechanics. The actual way that that comes about is incredibly interesting and subtle, and that's one of the topics of our research agenda in our Simons Foundation project, trying to understand what I'm not going to talk about today, but hopefully will in the future visit perhaps on spontaneous stochasticity. So what is then turbulence? So hopefully most of you know this already. In a pipe, the phase diagram is characterized by the Reynolds number, the velocity, characteristic length scale, the kinematic viscosity defined in terms of the molecular viscosity and density. Here's the Navier-Stokes equation. And round about Reynolds number 2000, there is a transition from purely laminar flow to fluctuating, unpredictable turbulent flow. And what I'm going to be talking about, I'll refer to this regime here above the transition as, quote, the life of turbulence, and this regime here where turbulence dies away as you go down in Reynolds number as the death of turbulence. Now, an important distinction between what I'm going to be doing and what is often done in talks by physicists, at least, is that you can see that I'm not doing three-dimensional, homogeneous, isotropic turbulence with periodic boundary conditions, which is what people, most of the papers are written about by physicists at least. And I think it's very important to emphasize that the boundary conditions here are not periodic. We have an open system of flow coming in, stuff coming out. And the point is that turbulence is generated by instabilities, both linear ones and long wavelength ones, and symmetry. Can somebody mute their microphone, please? It's distracting. So if you're not talking, please mute the microphone. Thank you. So symmetry is the enemy of instability, and so it's important if one wants to understand how turbulence is generated to have a mean flow. The other thing that's important, and this is something that Steve Tobias has worked a lot on and emphasizes in his work, is that turbulence itself interacts with the mean flow. So turbulence actually generates emergent mean flows, and these interact and feed back on the turbulence in very non-linear and complicated ways, which we are only beginning to understand. So I'll be talking about the transitional flow, I'll be talking about cascades, and I'll be talking a little bit about emergent mean flows. So if you ask, what does it mean to solve turbulence? Here's an answer. If you walk down the street and run into a physicist, she might say, well, why don't you try to predict the fluctuations in the velocity at small length scales? And that could be done. That, in fact, is the idea behind the Richardson-Kolmogorov cascade. So the idea is that if I put my fingers into the bathtub and stir the fluid around, you'll see swirly eddies spinning off smaller and smaller eddies, as shown schematically here, and they get smaller and smaller, so they go to larger and larger wave number. And in fact, this process is not a dissipative process at all, but is a Hamiltonian process. And that was the hypothesis that was due to Richardson and carried on by Kolmogorov. Now, the point is this: if it really is a Hamiltonian process, then viscosity will not enter into the equations that govern this, and that leads to a remarkable prediction, which is very closely satisfied by experiment. I want to just spend a couple of minutes walking through this because it relates to what I'm going to talk about later on in the talk. So if we talk about the energy spectrum, which is the kinetic energy per unit mass in the wave number range k to k plus dk, that's E of k, then it depends on the rate at which you are putting your fingers into the bathtub and stirring it around. So that's the energy input and the energy dissipated. Then there's the kinematic viscosity, and then there's the characteristic size of the system. Out of these variables, you can produce a length scale called the Kolmogorov length, which looks like this. And then once one does dimensional analysis, one finds without any further approximation that E of k has this form where f is a function to be determined. So the next thing that one does is one says, well, let's now take the wave number to infinity. We're going to be looking at large wave numbers. We're going to be looking at the small structure of turbulence. So k is going to infinity, and we're going to assume what the Russian applied mathematics school would call complete similarity. So we can take this limit and replace kl by its limiting value infinity. And so now we're left with this formula with now a functional dependence just on this. Then we want to look at what happens at large Reynolds numbers, and large Reynolds numbers means small viscosity, and small viscosity means eta going to 0. So we take the limit eta goes to 0, and again, we assume complete similarity in that. So we replace k eta by 0, and this is now just a constant. And what has to happen here is that eta is going to 0 here. So you might think that this quantity is going to explode, but this function here has an eta inside, and to make the new dependence cancel out, it has to have the following form, and so you derive Kolmogorov's law like this. So this is a very beautiful realization. We didn't even need to use the Navier-Stokes equations to derive this. In fact, much of what we understand about turbulence doesn't really come from Navier-Stokes equations at all. And so what it says is that there's going to be a range, which we'll call the inertial range of wave numbers, where at an intermediate range, you get this power law scaling. At high wave numbers, you enter the regime where molecular viscosity is important, and so you have dissipation. And at large wave numbers, that's where you're putting your fingers into the bathtub and stirring them around and putting in the energy. And so this is the characteristic shape of the energy spectrum. Now, unfortunately, this derivation is wrong, and it's wrong because at least one of these assumptions of complete similarity is not correct. So so this assumption here is not correct, and so one way that this limit can break down is that as you take this kl going to infinity limit, in fact the functional form is a new function of k of eta, but then kl raised to some power eta. And that's in Russian applied mathematics literature would be called intermediate asymptotics of the second kind. And if that is true, and you assume complete similarity as k eta goes to 0, which again, I don't know how to justify that, then you would have this functional form, a modification of Kolmogorov's 1941 scaling law, where the exponent 5/3 has now added an additional exponent eta, and eta is known as the intermittency exponent. Okay, so that's one view of turbulence. What about another one? So if you ask an engineer, they might say, well, you should predict the dissipation experience at large scales, because all I care about is I've got to design my car or my airplane or my the pump for an oil pipeline, and all I want to know is how much dissipation there's going to be. So the answer to that, and we'll return to this slide later in the talk, this is the friction experienced going of the pressure drop through a pipe. The friction factor, I'll define it later on, as a function of Reynolds number. And the most important thing you can see is that this is a very complicated functional form, and this is for different pipes of different roughnesses on their sides. We'll talk about that at the end of the talk, but you can see it's not a trivial dependence. And what one would like to be able to do is say, take these two separate questions and connect them together. So can you predict the dissipation experienced at large scales from understanding the velocity fluctuations at small scales? And that is a natural thing to expect, because you would think that the drag experienced at large scales would reflect the nature of the turbulent state at smaller scales. But how to make that connection an important puzzle which has not been addressed very much in the literature. And I'll call this, because this is fluctuations and this is dissipation, I'll call this a fluctuation-dissipation relation. That's what we would like to aspire to. And it's named that because of a similar kind of connection that is known in equilibrium statistical mechanics. Now, another way of thinking about how to solve turbulence would be to say, when and how do fluids become turbulent? And is there, in fact, some kind of universality at the laminar-turbulent transition? Universality meaning something generalizable that you can say, independent of the particular flow geometry. Now, transitional turbulence was first studied scientifically by Reynolds in 1883. And so what he does here is he takes his flow apparatus, which you can see illustrated here. He injects a little bit of ink so you can visualize the flow. And at slow speeds, the ink just traces out a straight line, a smooth, regular laminar flow. At higher speeds, the ink quickly breaks up into turbulent flow, jagged, irregular, and turbulent. But in between, you see the interesting situation where you have the flow is laminar, then something happens, some flashy thing that as Reynolds called it, or today we call these things puffs, then it goes back to laminar again, then more turbulence, then laminar, turbulence, and so on. And so you get this rather strange pattern formation structure going on at the same time as the transition. And you might ask yourself the following question. Here I am at low Reynolds numbers where the flow is laminar. Here I am at large Reynolds numbers where the flow is turbulent. And in between, there's some turbulence in the tube, but maybe not very much. So the question is, how much turbulence is there in the tube? And what you find from experiment, and I'll show you this later on, is that it follows the turbulent fraction follows the data shown here. And we're going to talk about that and what it means in detail later on. The point, though, is that because of the non-spatial uniformity here, where you have rare, sharp bursts of turbulence, the transition is a very complicated thing to understand. Now, what you may have noticed is that these two pictures are reminiscent of what happens in phase transitions. So if I look at the turbulence fraction as a function of Reynolds numbers, Reynolds number is your control parameter, that's kind of reminiscent of the order parameter in say, a magnetic phase transition. As you vary the temperature below the critical temperature, a piece of iron or nickel will suddenly become magnetic, and the magnetization goes continuously to zero as you approach the critical point, as you kind of see suggested here in the turbulence data. The other thing that you may know from phase transitions is that when you look at the fluctuations around a phase transition of, say, something like the magnetization typically, the fluctuations are correlated and they have strong power law correlations. Now, this energy spectrum is in fact a UK squared, so actually its expectation value is indeed a correlation function, the autocorrelation function of the velocity fluctuations. And so what that means is that we're seeing here some evidence of power law correlated fluctuations, again reminiscent of what happens at a phase transition. And in fact, this range of the inertial range that I showed you on a previous slide, I didn't say it then, but I should have done. The extent of this power law range depends on the Reynolds number. The smaller the Reynolds number, the smaller is this power law range. The larger the Reynolds number, as you go towards infinity, this range gets bigger and bigger and bigger. And that's exactly what happens in phase transition. So then, why is it that fully developed turbulence is hard? And why is this a hard problem that has resisted solution for so long? Well, if you look on page 191 of any good textbook on renormalization group, you'll find out that phase transitions are hard for the following reason. You have strong interactions of the order parameter and strong fluctuations. The fluctuation spectrum is very non-Gaussian and shows intermittency. And you might say, okay, that's fine, but you've got a small parameter. Why is this problem so hard? And the small parameter you might be thinking about is the fact that as I go close to the critical point, the temperature minus Tc over Tc, the fractional temperature difference, is getting smaller and smaller and smaller. So surely you have a small parameter there. Well, what you will find is that if I write down the free energy that describes the system very close to the transition and do the sort of dimensional analysis rescaling, what you find is that that all of these parameters here get replaced by unity, you're left with only one effective parameter that describes how the fluctuations self-interact. And that parameter, at least for dimensions less than 4, actually goes to infinity, not 0, as you get closer and closer to TC. And so you have a small parameter, but it's not a usable one. Now, when we look at turbulence, we have the same thing. We have very non-Gaussian fluctuations in the spatial gradients. We have bursts of weak fluctuations interspersed with bursts of strong fluctuations. And when we write down the Navier-Stokes equations and take the limit, nu goes to 0, or Reynolds number goes to infinity, again, the coefficient here, the coefficient in front of the only nonlinearity in the problem, becomes relatively large as the viscosity goes to 0. So again, we have no usable small parameter. Okay, so what we've said is we've mapped one hard problem into another hard problem. So did we make any progress? Well, perhaps, because the critical phenomena problem was solved by Ken Wilson, who developed renormalization group theory based on Leo Kadynov's and Ben Widham's data collapse and scaling ideas. And so we're going to try to follow that route in this talk. Okay, so now let's talk about the transition to turbulence. So I showed you how turbulence was measured, at least the transition was measured in the 19th century. This is how it's measured in the 21st century. So again, what I'm going to show you is data from our data from Björnhoff, who did an absolutely seminal experiment in 2008. And the experiment goes like this. Here's your pipe, and you're going to ask a different question. Instead of just looking at the turbulence and admiring it, what we're going to do is ask this question. Will a turbulent puff, if I inject it into the flow, which is otherwise laminar, it'll create some localized turbulence. How long will that turbulence live as the turbulence drifts down the tube and eventually comes out the other end? And there's two possibilities here shown in yellow and red. So what you do is you're injecting, the flow is laminar, you inject a little disturbance here that creates a localized region of turbulence, that's this red thing here. That turbulence creates increased drag, and if it lives to the time it gets out the other end, then the flow will come down and follow this red trajectory. If, on the other hand, it dies away before it gets there, say here, the velocity profile follows this yellow curve, and the fluid will come out along the yellow trajectory. And you can look at that and see which trajectory did it come out at, the red one or the yellow one. So you get a binary information. Did it survive, yes or no? And you know this as a function of the speed and this distance that it has to travel. And so you can measure the survival probability after many repetitions as a function of Reynolds number and as a function of time. So what do you get when you do that measurement? So what you see here is this is the turbulence intensity shown from a computer simulation. And what you see is that in this Reynolds number range, you create a puff and it will eventually die away as the probability of survival follows this law here. This is time on the horizontal axis. The logarithm of the survival probability on the vertical axis, you see you get a straight line for different Reynolds numbers. So it decays as e to the minus t minus of an offset over some characteristic time scale. And if you plot that time scale as a function of Reynolds number, you get the curve shown here. So this is the puff lifetime as a function of Reynolds number. And this is actually a semi-log plot. So what that means is that because this is curving upwards, a straight line on this curve would indicate an exponentially growing lifetime. So we can see that the lifetime here is actually growing faster than exponential. Now we can increase the Reynolds number a little bit further, above say 2050 or so, and now the puff not only can decay, but they can also split into two. And you can ask, well, what is going to happen to these splitting puffs? Well, what happens is this. Suppose I ask, how long does it take for a puff to split? Well, the greater the Reynolds number, the more likely it is to become turbulent. So the time between splitting events will be small. So what that means is that as I go to smaller Reynolds number, that time between splitting events is going to get bigger. And indeed, it does get bigger, and it gets bigger again with a curve that has upward curvature, indicating that it's going faster than exponential. And if I take the last refuge of the scoundrel and plot the double logarithm, what I see is the data are very straight. almost anything is, but here there is some meaning to this. And the intersect at a Reynolds number which we define to be the critical Reynolds number for turbulence. Above this critical Reynolds number, at long times, there will always be some turbulence in the tube, in the pipe. So what I've shown you then is that the characteristic lifetimes of turbulence have a superexponential scaling, which we can characterize as e to the Reynolds number. And we'll see where that comes from mathematically in a few minutes. So now I want to talk about a theory for this laminar turbulence transition. And to do that theory, I want to remind you of what happens in systems where we do know the answer, which is, say, a phase transition in equilibrium, let's say a magnet. So in a magnetic system, you have many different levels of description. And the lowest level is, of course, the electronic structure, the electronic band structure of the electrons and their spins as they move through the material. But that's too complicated, usually, to solve. So if one wants to understand the magnetic phase transition, we just focus on the electronic spins, and they obey a model called the Ising model. It's just an effective model for interacting with quantum spins. That model is too hard to solve. So what we say is, well, in general, let's throw away the quantum mechanics. Let's just make it classical, see if we can solve that. So now you've got a model of three-dimensional interacting spins, perhaps in an external magnetic field. And that model is also too hard to solve. And so what you do is then you try to write down an effective free energy that governs the magnetic behavior of the spins in the vicinity of the phase transition. And that's the so-called Landau theory. I showed you that on one of the previous slides. That theory then is possible to solve using renormalization group methods, and we can learn about the universality class, the critical exponents, and the phase diagram of the system. So that's what we do in equilibrium. And what we measure is the magnetization as a function of temperature. And as you go down in temperature, the magnet has as many spins up as down. But as you go below a critical temperature, then you start to get a few more spins pointing in one direction than another. And so the magnetization quickly rises in some way that it is the task, excuse me, in a way that it is the task of phase transition theory to determine. And that's the thing we want to understand. And these modes very close to the transition are weak and they're long wavelength, but they contribute to thermodynamic singularities. So for example, you might think that this shape of this curve would be some kind of parabola very close to this transition, but in fact it is non-analytic. The magnetization rises as a non-analytic power of the temperature difference between the temperature and the critical temperature. And this is true when there's no external field and you take the temperature going to Tc. So that's one stylized fact. Another stylized fact is you can ask the following question of a magnet. Let's have a magnet just sitting there with spins flipping up and down, and now I apply an external magnetic field. Well, some of the spins will start to point in the same direction as the field. So how much magnetization will that external field generate? Well, what you would say is the number is going to be proportional to the external magnetic field, and that indeed is Curie's law. And it's just a statement of linear response theory. The bigger the external field, the bigger the response. But that breaks down also at the critical point, and in fact, the relationship between magnetization and external field is also non-analytic at T equals Tc. And what Widom and Kadanoff understood was that these two stylized facts can be combined into a functional form, ostensibly a function of two parameters, but really now a function of just one combined similarity parameter, and you can derive these results from this functional form. And indeed, this functional form makes a prediction. So here is the magnetization scaled in the way that the theory that Kadanoff came up with suggests. This is the temperature scaled in the way that the theory predicts. These are 5 different magnetic materials, and you can see, even though these materials have very different critical temperatures and have very different electronic structure and everything, the data for the magnetization all falls on one curve. And this solid line that goes through the data is the renormalization group prediction, where there's no adjustable parameters in this curve, and it fits the data beautifully. So this is what we'll call a data collapse, and it shows you a universality. in several manifestations, namely that this function is independent of what happens to the particular materials, what type of materials they are, and so on and so forth. Okay, so this is a very remarkable discovery, and it led to the renormalization group. But we're going to come back to that in a little bit later in the talk. So now let's talk about turbulence. So in turbulence, at the lowest level of description, we have particles bouncing around in a box. We can coarse grain that and get a description which is the Navier-Stokes equation, say something roughly like the Ising model. But we know that we can't even solve that in equilibrium phase transitions. We have no hope of solving this for something non-equilibrium like turbulence. So then our next path of defense, as it were, is to say, well, okay, well, what is the analog of Landau theory? What is the analog of the renormalization group universality class? And so what I'm going to talk about is this. I'm going to now try to construct for you the Landau theory and work out the renormalization group universality class. Now, of course, to do that, we have to follow what phase transitions tells us, which says if this is a phase transition, a non-equilibrium phase transition, what we should do is identify the long wavelength collective modes of this transition. And we have no hope of being able to do that analytically, so we're just going to use direct numerical simulations of the Navier-Stokes equations. So you go and do that. We use open pipe flow code from Ashley Willis, which is a pseudo-spectral code. Everybody uses it. And what we discovered, to cut a long story short, is that there are two important modes near a transition. So on small scales, as one would expect, you have turbulence shown in green here. But what we discovered was that there's a weak long wavelength azimuthal mode, which is really a zonal flow, which has structure in the radial direction, no structure in the streamwise direction, and in fact is time dependent. And if we plot the energy in these two different modes, what we see is that the energy is oscillating and follows a roughly pi/2 phase shift. Now, the reason for that is possible to understand, because what is happening is that the anisotropy of turbulence locally, if you just took a snapshot of a cross section of the pipe, you would see that there's some anisotropic distribution of turbulence, and so that means that the Reynolds stress, which is shown here in terms of the velocity fluctuations in the plane polar coordinates, generates a mean velocity in the azimuthal direction. You can just derive this from the Reynolds stress equations. So what that means is that the Reynolds anisotropy generates this azimuthal flow, but that azimuthal flow shears the turbulence, and by shearing it, makes it more isotropic. So the turbulence induces the zonal flow, but the zonal flow suppresses the turbulence. And by suppressing the turbulence, that suppresses the zonal flow. And by suppressing the zonal flow, which is restricting the turbulence, that enables the turbulence to rebound. And so you get these series of oscillations, which are very reminiscent of what happens in a predator-prey system, where the presence of prey allows a predator to grow its population. But once the predator population grows, it suppresses the prey by eating them all. There isn't enough food. The predator then starves, and you go back to the original situation. So what I've argued for you then from these numerical simulations is by identifying these important modes, what we have found is that there's an analogy between a predator-prey ecosystem and its pi/2 persistent fluctuations and the pi/2 persistent fluctuations in the pipe flow near a turbulence in this sort of two fluid model caricature of what's happening near the critical point. So let's now think about how we would describe a predator-prey system, and the way that we do it in statistical mechanics. And again, this is something that Mauro Mobilia, who I hope is in the audience, is also one of the pioneers and an expert on this, and we will actually use some of his work later on in the talk. So the idea is that we think of the predator A and the prey B as being particles that just sort of move around in the ecosystem, and whenever a predator encounters a prey, so that's A plus B, then with some probability P, the predator eats the prey and then has enough energy to make a baby predator, so A plus B goes to 2A. And there's similar other reactions here. So this is the prey eating food and producing a baby, another baby prey. These are predators competing for food, and these are death processes. And and it's a long story to explain this, a whole other seminar, but basically, if I look at the time series that it generates, and I solve just the Lotka-Volterra equations, the mean field equations that derive from these stochastic differential equations through, say, a Van Kampen expansion, those equations have a deterministic fixed point, which is not persistent oscillations, but the stochastic system always has these persistent oscillations. And so we're going to take that and use that to construct a Landau theory. Now, the idea is this. I'm going to show you here a sort of dictionary. So what I've shown you is that you have a zonal flow and you have turbulence. I'm going to represent that by a wiggly line. And what we're going to do is write down Feynman diagrams that come from the Navier-Stokes equations. So the Navier-Stokes equations have a second order nonlinearity from the advection term. And so that means that when you write down a perturbations theory, every vertex is going to be a 3-point vertex like this. So you can write down every possible diagram that you can think of, and indeed there are rules that go from these diagrams to actual integral equation solutions of the Navier-Stokes equations. If I take these pictures and then look at them in terms of the predator-prey description, if you want to think of this as wave-particle duality, you can do so. So let's look at this diagram here. This says turbulence encounters a zonal flow. The zonal flow suppresses the turbulence and produces more zonal flow. That's this reaction A plus B with some probability P goes to A plus A, and the same for all these other reactions. So one can write down all these processes, and so one can write down a predator-prey model for turbulence near its transition. And just as a side note, the first person to realize that you can make a Feynman diagram expansion of the Navier-Stokes equations was Bill Wild, who was my colleague here at the University of Illinois until he passed away about 10 years ago. Okay, so what I've told you now then is that we can regard the Landau theory for laminar turbulence transition as being some kind of stochastic predator-prey model. And so what I want to show you now is this. Put aside the Navier-Stokes equations, let's just look at this stochastic predator-prey model. And what I'm going to show you is that it recapitulates everything we know about the turbulence data in a pipe, namely the phase diagram, the lifetime statistics, and we can determine the universality class. So here is the phase diagram I already showed you for pipes. So here's the Reynolds number. In this regime, you have metastable puffs that decay. In this regime, you have puffs that split in some way, and here's a regime I'm not going to talk about. This is a predator-prey model, but now the axis is the prey birth rate. Because think about it like this. If the prey make babies, let's say once every 100 years, okay, so the wolves come in, eat the sheep don't make any babies, and so the whole population will go extinct. The sheep are eaten, and then the wolves have nothing to eat, and so they die away as well. If, on the other hand, the prey make babies, every 10 minutes or so, then of course there's always a good supply of food, and so the predators can eat lots of babies and lots of food, and the population never dies out, and so you get coexistence. So as you vary the prey birth rate, you go into a regime where you have coexistence, and in fact, when you simulate this in a pipe geometry, you start off with a spatial uniform mixture of predator and prey. It self-organizes, and you form these metastable puffs that decay away. And at higher birth rate, you actually get an instability to a pattern-forming instability to splitting populations, which is just like what happens up here with the puffs. So let me show you the world lines of that. So on the right here, this is time as a function of space. The color scale is the turbulent intensity, and these are from numerical simulations of pipe turbulence. So here you have a puff that's going along, and then at this time here, it splits into two, and then this puff itself splits into two, and so on and so forth. here's what happens in the predator-prey ecosystem. So the color scale now is the prey population density, and you can see that you have a puff, and then it splits into two, and then that splits into two, and so on, and you get a series of bifurcations. So then you can say, well, given that, why don't I measure two things? I can measure the extinction time of the prey in this regime, and I can measure the time between population splitting events in the splitting population regime. So let's go ahead and do that. So you do it. And this is what you find. So here is the, which one is which? This one is the, I always forget. This is the prey. Yeah, this is the ecosystem one. So these are the data I already showed you from turbulence, showing you this upward curving super exponential behavior. And here's what happens in the predator-prey system, again showing you this upward curving super exponential behavior. So what we've learned then is that the extinction in ecology is the same thing as the death of turbulence. As you go from high Reynolds number to low Reynolds number, the turbulence dies. As you lower the birth rate of the prey, the ecosystem goes extinct. And these two transitions behave exactly the same way. So just to recapitulate, we started off with Navier-Stokes. We came upon a two-fluid model looking at from the idea of thinking about phase transitions. We identified the two important modes, but the question we really want to understand is, what is the universality class? And what I'm going to show you is that that universality class is directed percolation, and we're going to understand that from work that was done many years ago, 13 years or so ago, by Mauro Mobilio and others, showing that this stochastic field theory maps into what's known as Reggian field theory. It's a field theory from hadron scattering in particle physics, and that is in the same universality class as another model in statistical physics known as directed percolation. So we're going to go around this diagram like this, and I'm going to explain this to you not with path integrals and so on, but just in a very simple, intuitive, pictorial way. Okay, so what is directed percolation? So directed percolation is what you do every morning when you make your coffee, as I've just done, because it's morning here in Urbana-Champaign. So what you do is you, if you're like me, you get your conical flask, you put in some filter paper, you pour in some coffee, and then you pour in some hot water on top of it, and the water dribbles through, as shown schematically here, with some probability P. It can dribble through the gaps between the coffee grains, and that P will depend on how closely packed the coffee grains are. So if you just pour the coffee in and then just pour the water in, what will happen is the water quickly trickles through and you get a cup of coffee. And that cup of coffee is what you can experience if you want, if you go to any petrol station in the US or maybe in England as well, you get a weak, unsatisfying cup of coffee. So then if you're like me, you'll say, well, that's no good. So I'll sort of try to crush the coffee grains together to try to get the water to go through the coffee grains much more slowly, and therefore absorb all the good stuff. But then what happens is, of course, that you've overdone it. And the water can't find its way through. It's like I've shown you here. It gets stuck at this point here. And as the more water you pour in, it starts to back up and then pours all over the counter. And then everybody starts shouting at you. And it's a very unpleasant way to start your day. So that doesn't work either. And so what you try to do is compress the coffee grains, but not too much. You try to find the just right solution so that the coffee does manage to go all the way through, but as slowly as possible. Now, if you look at the paths shown here by the percolating process, you can, if you look at it carefully, you can see that there's really two types of node here. So these diagrams show you the system at time t and the system at time t+1. So one thing is that you can start off with a filled node. There's coffee here. It's not able to percolate through to the next site because the percolation probability of finding that path is too small. So that's what we call annihilation. What can happen is that the fluid can actually go to two neighboring sites, like I've shown here, and that we'll call decoagulation, or it can just simply hop and diffuse around in this porous medium. We'll call that diffusion, or it can coagulate. I don't think I have that shown here. No, I don't. But anyway, two of these filled ones flow into just one filled site here. So those are the four basic processes, and from that you can construct all of these possible ways of seeing things. So now if we look at the patterns produced by this process, so this is time along here, this is space, and the filled squares, filled pixels, show you occupied sites, or in the turbulence language, regions where there is turbulence. And you can see that at long times, if the percolation probability is too small, then there's no, at long times you've not got any filled sites in the system, so it didn't manage to get through. On the other hand, the weak American petrol station coffee is that it flows through very quickly. All the sites are filled. You've got the fluid flow through to the other side, but it went too quickly. And then this here is the perfect cup of coffee, where the fluid just manages to find a way through the system. And at long times, there's a small amount of occupied sites in the system. And this behavior is characterized by universal exponents. So very close to this transition here, the turbulent fraction, with the number of occupied sites, scales like P minus PC to the beta. The correlation length has this anisotropic behavior that I'm not going to get into. And in general, we understand this process extremely well. So here I'm showing you a simulation of directed percolation in a pipe geometry in 3 space and 1 time dimension. And you can see here the last remaining site is, in fact, if I look at it in, say, 1 + 1 dimension so I can see it more clearly, the last remaining pixel of turbulence is the longest path that you have going through the system in this anisotropic directed percolation system. So because of that, what that says is that the time that the turbulence takes to decay away is determined by the longest path here. In other words, roughly speaking, if you think of these sites as being independent and you're looking at percolation from several independent sites, it's the longest path, the maximum one, amongst a bunch of independent random percolating paths. And so that tells you that the statistics of the lifetime of turbulence will be governed by extreme value statistics, not the central limit theory. So in other words, if I want to know the probability density or the cumulative distribution for a random variable that is made up of the maximum of a bunch of other random variables, then for the system that we're talking about here, there's in fact 3 different universality classes for this, all worked out by Fisher and Tippett and later Gumbel, and the one that we're concerned with is this one whose cumulative distribution is this double exponential form. And this, roughly speaking, is where that super exponential form that I showed you earlier comes from. It's not quite as simple as that, because near the phase transition, the correlated fluctuations are not IID variables, but that's something that's beyond the scope of this talk. So now let's look at the universality class of the predator-prey ecosystem near its extinction. So what I've shown you here are the same chemical reactions, if you will, for the predator-prey ecosystem that I showed you before, but now we've got an extra index here. I and J represent neighboring sites in our physical system, in our system where the predators and preys are hopping around. So they're spatial indices. Now what's going to happen is this, very close to a transition, the predator cannot survive. Its population is reliant on the already small prey population, so we'll set its population equal to 0. So we're going to go from a 3 trophic level ecosystem to a 2 trophic level ecosystem, where you have the food, which is the energy in the laminar flow, and then the prey, and then the predator is now ignored in this. So now we'll throw away those diagrams. And then what do we have left? What we have left then are these 4 processes. And if I draw those processes diagrammatically, you see that these are the 4 processes, the diagrammatic processes of directed percolation. And so what we've learned is that near the extinction transition, the stochastic predator-prey dynamics reduces to directed percolation. Okay, so that's interesting prediction. So is it true? So these are data from Björn Hoff's group, again, another beautiful experiment in 2016. This is a Taylor-Couette system. It's a very, very narrow system, very long aspect ratio. In other words, the distance around the circumference is much greater than the height here or the separation between the plates. And the outer plate is rotating, the inner one is stationary. And if I just look at the, I shine a laser light on the system and look at the light reflected, if the flow is allowing the particles all in one direction, so I get this white, bright reflection. But if there's some turbulence, then the light is scattered in different directions, and so I get these black bands. And so as the fluid rotates, takes one rotation, two rotations, three rotations, I see these sequence of pictures here, and it may look as if these turbulent bands are stationary, but if I take these pictures for each of these strips and stack them up one underneath each other, what I get are the pictures shown here. So blue is the turbulence, yellow is the laminar, and you can see that these world lines, if you will, of the turbulence map out pictures that look very much like a directed percolation. And indeed, if you then go and measure the turbulent fraction and measure the critical behavior, you find that it fits very well the predictions from directed percolation for this turbulent fraction as a function of Reynolds number. Similarly, there's another nice computer simulation done by Chantry, Tuckerman, and Barclay, published a couple of years ago in JFM. They looked at a stress-free planar shear flow and also observed the exponents of 2 + 1 dimensional directed percolation. How about the predator-prey dynamics? Well, those have also been observed, not in pipe transitional turbulence because it's too hard to see, but in MHD systems, in particular tokamak, you have a drift turbulence that goes around the axis of the toroid of the tokamak, and a zonal flow that goes around the outside, and the predator-prey oscillations, which were predicted back in the 90s by Pat Diamond and colleagues, were observed in this paper by Strada. So what I've shown you then is that in transitional turbulence, it's a non-equilibrium critical point in the universality class of directed percolation, and we've seen this both computationally and experimentally. So now I want to end by talking about fluctuations and dissipation. So I showed you at the beginning what I consider to be one of the most interesting experiments in fluid dynamics, which is this experiment by Nikoradze from 1933. So he took a pipe and glued monodisperse sand grains to the sides of the pipe. And what he did was he measured as a function of the pressure drop per unit length, normalized by the kinetic energy per unit mass of the flow, the mean flow velocity u. He measured that pressure drop and normalized it in this way to get a dimensionless friction factor. So these are his data here, and he did this as a function of ratios of the grain size to the pipe diameter. So he varied the roughness parameter. So what you're seeing here is the logarithm of the friction factor as a function of the logarithm of the Reynolds number. The smallest friction is when the pipes are the smoothest. The largest friction is when the pipes are roughest. And so that's the sequence of pictures you have here. Now this regime here is the laminar regime. What you can see happening is that the friction factor goes down with a power law -1. And the reason it's -1 is that in Stokes flow, the friction factor is proportional to the velocity, or in other words, the Reynolds number, but you're normalizing by the velocity squared, so you get a 1/Reynolds number. Then here you have the transition to turbulence, which is what we've just been talking around about 2000 or so. And then you have a regime where as you go to smoother and smoother pipes, the friction follows further and further in Reynolds number, this straight line law, which has a slope of -1/4. And this is called the Blasius regime. Then something weird happens over here, this non-monotonic behavior. And then finally, at large Reynolds numbers, the friction factor becomes independent of Reynolds number, but then only depends on the roughness. And if you plot how it varies on this roughness, it scales the roughness to the 1/3 power. These are two stylized facts, and they are similar to the stylized facts that I showed you in critical phenomena. So we're going to ask the questions, is the behavior above the critical point, is that also a critical phenomenon? So let's just clarify this question. In critical phenomena, I already showed you that the correlation functions scale as k to the -2. At least I told you that it's something that's well known and easy to understand. And I also showed you the data collapse that was predicted by Widom and Kazanov. In turbulence, you have this analog of the correlation function, power law scaling, which is E of k. And so my question is, what goes in this box here? What is the analog of the data collapse for large-scale thermodynamics that you have in critical phenomena? What is the analog of that for turbulence? And this is the thing that I want to find the analog for in turbulence, just to remind you. So to cut a long story short, I'm not going to have time to go into how we got this result. But the answer is that the scaling that you would predict, if you think of turbulence, fully developed turbulence, being controlled by a critical point, is that the friction factor should scale with this law here, where eta is that intermittency exponent that I told you about at the beginning of the talk. And if I plot the data in the same way that I showed you we did for the magnetic phenomena, you see that all these data collapse onto one universal curve, and you can extract the intermittency exponent and get a value consistent with spectral estimates. So we do indeed see this data collapse formula, and so that's what goes in this box here. This is the analog of Widom scaling in phase transition. So this is absolutely remarkable and fantastic, and I'll tell you why. Just think about it this way. All Nikoradze did in 1933 was measure the pressure drop across a pipe. But from that set of data, interpreted through the lens of statistical mechanics by me 80 years later or more, what one can extract is the anomalous spectral exponents. And they were measured 8 years before Kolmogorov's mean field theory. So it's absolutely fantastic that from just the measuring of friction, you can deduce the intermittency corrections to the velocity fluctuations. And this connection between the dissipation and the fluctuations is what in some of our papers we call the spectral link, and it's a fluctuation-dissipation relation. So where do these exponents come from? And again, I don't have time, that's a whole other seminar to tell you that, but this is really work that started with Gustavo Joya and Pinaki Chakraborty, and their paper came out in the same issue of PRL as my paper on this data collapse scaling. And what ends up being the case is that the friction factor, the dissipation, ends up depending on the energy spectrum in the way shown here. And so this is this fluctuation dissipation relation. We don't understand this rigorously. We only understand it heuristically, and our understanding is imprecise. And that's one of the topics of our Simons project. Now we tested this experimentally in 2 dimensions. And as many of you will know, in 2-dimensional turbulence, there are 2 types of cascade. It's not universal. There's an inverse energy cascade, which has the same wave number dependence as the 3D Kolmogorov cascade that I showed you before. But there's also a cascade of entropy. Entropy, this is the integral of the vorticity squared. And because, well, anyway, it doesn't really matter why. And you can show fairly easily that the energy spectrum for that cascade has a different spectrum. It goes as k to the -3. So given this connection between the energy spectrum and the friction factor, you would expect that there would be a different Reynolds number scaling for the entropy cascade compared to the energy cascade. And when you work it out, these are the exponents that you get. A half here rather than 1/4 for the Blasius regime. Okay, so we did this experiment with Walter Goldberg and Hamid Kelly and others. We made a 2-dimensional turbulent soap film as shown here. It's a gravity-driven flow. It's protected by perspex sheets to prevent air currents. We fire lasers at it to do LDV and can measure the velocity profile. And from that, we can measure the energy spectrum and the friction factor. So here, for example, is a setup with a grid showing you that we get an entropy cascade with an exponent k to the -3. Here is a different setup where shown here where we have saw blades on the side that give you a roughness, nothing on this side, and even without a grid, what you find is a spectrum that decays as k to the -5/3, consistent with, but not proving that the direction of flow is inverse, but suggesting it of k to the -5/3. So that says then that if we now look at the friction factor in these two different geometries, we should see different scalings of the friction factor with Reynolds number. And indeed, for the energy cascade, the inverse energy cascade, we see the predicted exponent of 1/4. And for the for the forward entropy cascade, we see the exponent of 1/2, just as predicted. So what I've shown you is that the drag experience at large scales does reflect the nature of the turbulent state, both from the theory and then from these experimental verifications. So I'm going to skip this part, and I'm going to conclude. So the take-home message is that there are two types of universality in turbulence. There's two types of fixed point, one here at large Reynolds numbers that controls this regime, one here at small Reynolds numbers where you have a non-equilibrium phase transition from laminar to turbulence. Each of these critical points has their own scaling laws, crossovers, and universality classes. And in this regime, one has the unifying concepts of fluctuation, dissipation, rare events, mean flow interactions, things that I haven't had time to talk about. So here are the people who worked with me on this, and this is where did my mouse go? What a time for my mouse to turn out. Okay, here's a bit of scientific tourism. So if you go to Manchester, easier for you to do than for me to do. Go to the basement of the mechanical engineering department, you will find Reynolds's original apparatus. And here is me and Hongyan Shi standing in front of that. This is Songlin, an undergraduate who worked with us on this. So I want to end with a comment. So this is a fortune cookie, and I actually got this fortune cookie. I am the single best person on the entire planet to get this fortune cookie, because it says turbulence is a life force. It's opportunity. Let's love turbulence and use it for change. And the reason that I'm bringing this up is there's an interesting philosophical point here. So usually in physics or biophysics, what happens is somebody gets up there and they say, I'm a physicist, I'm going to tell you something about biology. I built a better microscope. I built a better computer simulation. I used physics to then see something in biology that you couldn't otherwise see. And we're very used to that. But here we did the other way around. We actually worked on the biology problems, the population dynamics problems, and we simultaneously worked on turbulence. And the big surprise was that we were working on the same problem. We were able to understand this turbulence problem because we had understood something about the biology first. And so that was a very unusual situation. And in fact, Hongyan Shi won the APS dissertation award for her work on both the population dynamics and the turbulence. So here are some references to the works I talked about, and I'll be happy to take any questions.
Thank you, Nigel, for a wonderful talk and also giving us the lottery numbers for this week.